All right, let's start now with something called empirical probability. All right, you know how with rolling a die or tossing a coin, you know what all the possible outcomes are, and we have this sense that they're all equally likely, so it makes it kind of easy to figure out what the probability for various events would be. But that's not always the case. I'm using an example later where I'm tossing like a red solo cup in the air. And so it might land on its side, it might land upright, or it might land with the top of the cup facing down. We don't have a mathematical way of calculating the likelihood of any one of those outcomes. But what we could do is toss the coin a bunch of times and see how many times it landed face down, how many times it landed on its side, etc. And when we do that type of thing, we're performing experiments in order to figure out what the likelihood of a certain outcome, of a certain event happening would be. Okay? All right, so here, instead of counting equally likely outcomes with empirical probability, we're using data from an experiment to figure out the likelihood of something happening. So the first example we're talking about is maybe 100 games into the season, your favorite baseball team has won 60 games and lost 40. So since they've won 60 of their 100 games so far, we could say the probability of them winning a game is about 60 out of 100, or 0.6. Okay, that's what we're talking about with empirical. So it's based on, empirical with an I right there. I always want to spell it with an E for some reason. Empirical probability. So it's based on observed frequencies. Okay. But it just think of it as based on observed results, like looking at what happens and having recorded what happens. Okay, let me write that so you can read that better. It's called frequencies, is the official. Frequencies. IES. So that's the number of times a particular event has occurred out of a certain number of trials. Okay. So some of the letters used are the same as before. So the probability of an event happening, so that's the same notation as before. With this type of thing, it's just going to equal how many times the thing you wanted to happen happened. So you just count how many times did you get the result you wanted. Okay. So like if I wanted to know what's the probability a cup is going to land on its side, I would have just tossed the cup a bunch of times, maybe 100 times, and just recorded how often it landed on its side, and then I could use that as an estimate for the theoretical probability. Okay. So we count up how many times the various possibilities happen, and then we can use those to make predictions on what the probability would be. So it's kind of like just an estimate of what you think the theoretical probability would be. So like that baseball problem from before, it can be written in the form of a frequency distribution. That's just a table where you've counted up how many times certain things happened. Okay? So like if you're interested in how often they win, how often they lose, then you could just come up with the categories you're interested in. So that's winning and losing. You saw that they won 60 times, lost 40, and the total number of games played was 100. Then the probability that they're going to win, we could determine by the fact that we counted that they won 60 times out of the 100, and that turns out to be the same as 0.6 or 3/5. Okay. All right, now my father-in-law, he was a plant breeder, and so they would come up with various new types of, he did clover, and then what they would do is they would plant them, and then they would estimate how many of them actually germinated, just means how many of them actually sprouted. And of course, the more that sprout out of the number planted, then that's a better situation, a better what you're looking for. And so they might actually report that. That might be something they advertise on the bag of seed that they're selling. So here our question is, find the empirical probability that any particular seed of this type will germinate. So somebody planted 200 seeds, they found out 175 of them germinated. So you would just take the 175 out of the 200 and then just simplify that. So that winds up simplifying to be 7/8. Okay. All right, now here's a plastic cup example. So let's suppose somebody's tossed one of those plastic cups, landed on its side 44 times, it landed on its top 5 times, and it landed on the bottom just 1 time. Okay? So find the probability that the cup will land on its top the next time it's tossed. So that's like, what's the likelihood it's going to land on its top? So there's no mathematical determination of this that we could do to determine the theoretical probability. But what we can do is say, well, it landed on the top 5 times out of 50 times we tossed the cup. So we'd expect it to land on its top a tenth of the time. Okay, so it's almost like there's a 10% chance that it's going to land, not a 10%, yeah, 10% chance that it's going to land on its top. Okay. All right, I'm going to go ahead and do some of the fundamental counting principle in this video also. All right, so how many possible outcomes we have, like when rolling a single die, the number of possible outcomes, the 6 that we get, oftentimes is the denominator of our probability problems. So remember back here, okay, when we were coming up with, here we go, this problem, the number of possible outcomes is oftentimes, or is, the denominator when you're doing theoretical probability, the number of outcomes in your sample space. So with rolling a die or tossing a coin, it's pretty easy to figure that out. But sometimes you have lots of different outcomes. Your sample space is much larger than that. And it might be hard for you to actually list them and count them. So you want to have some other way of figuring out how to come up with the possible outcomes and how many there are. Okay? Because if you that number is going to turn out to be the denominator when you are asked a probability question. So here's where we're going to talk a little more about a tree diagram and then this concept called the fundamental counting principle, which is a way of coming up with how many different possibilities there are in your sample space. Okay, so here the question we're investigating is, at this particular store, okay, you're trying to choose a couch and you've got some possible choices. So first you have to pick the type. So maybe you are going to choose between leather and micro suede, and then you have 4 different colors to choose from, tan, white, red, or green, and those are for each one. And then the question is, how many different couches do you have to choose from? All right, so you notice if we did that, there were 2 possible choices, okay, for the, I guess I'll say fabric, okay, and then there were 4 possible choices of color, and that gave us the 8 possible choices. See the 8 end results? So it's like it could be tan leather. Okay, so it might be a leather couch that's tan, or it might be a leather couch that's white, or it might be a leather couch that's red or green, etc. Or maybe you went the micro suede route and picked tan, white, red, or green. So all total, there's 8 possible couches that you could wind up choosing. Okay? And the different options for the fabric, I'll say, was 2, and then the different options for the color was 4, and so you wind up having those 8 possibilities. This right here is called the fundamental counting principle, this idea of multiplying 2 times 4 to come up with all the possible outcomes, okay, is what we're actually describing in this section. It's very useful because that number a lot of times will be the denominator of a probability question. Okay. All right, now we got to where we had 8 possible couches. See how there's 8 ending branches. Okay. What if we also know it comes with or without a recliner? Okay. So let me add that in. So if we did recliner or no recliner on each of these, recliner or no recliner, do you see how that would now expand the possibilities to 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possibilities. I'm going to write this vertically, though normally you don't. So there were 2 types of fabric times the 4 different colors, and then times 2 options for whether or not you had an end recliner, and that 2 times 4 times 2 would now get me to 16 possible couches. Okay? All right, so that's the idea behind the fundamental counting principle, and the usefulness of the tree diagram cannot be I cannot say enough about how helpful it is to understand how to come up with all the possible outcomes. Not just how many, but actually know what they would be. So, you know, I could list all 16 of these. I'll list just a couple. So here's one outcome. Leather, tan, no recliner. That's one sofa right there. So that was going down here and then taking that branch. Okay, well, if I did that with every possible thing, okay, so like kept going, then there would be a list of 16 different sofas when I'm finished. Okay, but having what they are is really helpful when you get asked your probability questions. All right, so I'm going to stop this video as soon as I finish question number 8. All right, so the fundamental counting principle just says, if we're doing a sequence of things like choosing a fabric, then choosing a color, and then choosing whether or not we have an end recliner, okay, what we can do to figure out the total number of possible ways we can do all of those procedures would be count up, well, how many options was there for the first thing we had to do, which was picking a fabric? How many options for the second decision we had to make, which was choosing a color? How many options regarding the recliner at the end, whether it had one or not? And then we can just multiply all of that to get the total number of possible outcomes. Okay? All right, so here's a question that deals with that. So there are 4 basic blood types, A, B, AB, and O. Then there's an RH factor. Okay, so that's represented by a plus or a minus. And then let's suppose that a blood bank is going to label the donations with the blood type, the RH factor, and the sex of the donor. So we want to think about how many different ways a blood sample could be labeled. So they have what type it is, then the RH factor, RH is capital R, lowercase h, RH factor, and then they have the gender. Okay, so there's there's 4 types, AB, and O, so there's 4 possibilities there. For RH factor, there's 2 possibilities, and for gender, there's 2. And so 4 times 2 times 2 happens to be 16 different ways those blood samples could be labeled.